Tonight, we are going somewhere. Not somewhere you can find on a map, not somewhere you can drive to, or take a train toward, or book a flight and arrive at before the morning is done. Tonight, we are going somewhere that exists beyond the reach of everything familiar, beyond the warm glow of your window, beyond the last city light you've ever seen from the edge of a dark hillside on a quiet evening. Tonight, we go outward. And as we go, as we drift gently through the pages of distance and time, something beautiful will begin to happen. The world behind you will grow smaller. Its noise will soften. The weight of everything you carry will begin to ease, because space, true space, has a way of doing that. It has a way of reminding you, quietly, without urgency, that you are a part of something so vast, so unhurried, so endlessly patient, that your own worries are held within it like a single grain of sand is held within the ocean. Not dismissed, not diminished, simply placed in perspective. So breathe, just a little more slowly now. Let your shoulders settle. Let your eyes grow heavy, if they wish. We have time. All the time in the universe. And before we begin this long, slow journey outward through the dark, I want to gently invite you to stay with us tonight. If this kind of calm, this kind of slow and thoughtful voyage through the cosmos is something that soothes you, something that helps the day release its grip on your mind, then consider sharing it with someone who might need the same quiet. Leave a thought if you feel moved to, and simply allow yourself to be here, fully here, in this moment, before we lift off together into the silence between the stars. Because what we are about to explore is one of the most quietly astonishing questions a human mind can hold. How long does it actually take to travel from where you are right now, from this small, warm, breathing planet suspended in the dark, to each of the other worlds that orbit alongside us around the same gentle star? Not in theory, not in imagination, but in real, honest, humbling time. And the answer, when you truly let it settle in, when you allow yourself to feel the distances rather than simply hear the numbers, is one of the most peaceful revelations the universe has to offer, because it tells you something true about the nature of space itself. It tells you that the universe is not in a hurry, that the distance between worlds is not a problem to be solved, but a meditation to be experienced. A reminder that existence is large and we are small, and that smallness is not a weakness, but a kind of miracle. Let us begin where we always begin. At home. Close your eyes for a moment, if you haven't already. Imagine you are standing outside, just where you are right now, but the city or town or countryside around you has gone quiet. It is the middle of a clear, windless night. The air is cool and still. And above you, the sky has opened up in a way that only happens far from lights and noise. A great dark canvas scattered with more stars than you could count in a lifetime, arranged in patterns so old that ancient civilizations built their entire understanding of time and meaning around them. You are standing on the surface of a planet, a living, breathing, spinning planet, third from a medium-sized, middle-aged star, located in a quiet suburban region of a spiral galaxy called the Milky Way. You are on Earth, and right now, at this very moment, as you breathe and settle and allow the weight of the day to dissolve, this planet is moving. It is spinning on its axis at roughly 1,000 miles per hour at the equator, and at the same time it is hurtling around the sun at nearly 67,000 miles per hour, and the sun itself is carrying us all, this entire solar system, through the galaxy at roughly 500,000 miles per hour. You feel none of this. You feel only stillness. And that, in its own quiet way, is the first wonder of the night. But now imagine lifting off. Imagine rising gently, effortlessly, the way you might rise in a dream, upward through the cool air, through the thin layer of clouds, if there are any, upward through the atmosphere, that impossibly thin shell of air and warmth and life that wraps this world like the skin of a peach. And then, suddenly, the sky darkens. The blue fades into the deepest, most perfect black you have ever seen. And the stars stop twinkling. They become fixed, sharp, unwavering points of ancient light. You are in space. And from here, from this vantage point just above the world that made you, the question unfolds in all its quiet immensity. Where do you want to go? There are 8 planets in our solar system, not counting the world you just left behind. 8 different worlds, each one a destination, each one a journey measured not in hours, but in months or years, or in some cases, in decades. Each one with its own character, its own silence, its own strange and alien beauty waiting in the dark. And the distances between them are not what most people imagine. When we see illustrations of the solar system, those familiar diagrams with the sun at the center and the planets arranged in neat, concentric rings, we are almost always looking at a lie. A beautiful, necessary lie. Because if those diagrams were drawn to scale, if they showed the actual distances between the planets, most of the image would be empty. Most of the page, or the screen, or the wall would be nothing but blank, empty space. The planets themselves would be invisible. Dots too small to see, scattered across an emptiness so profound that the word vast begins to feel inadequate. But this is not frightening. This is, in a strange and quiet way, comforting, because the universe is mostly space, mostly emptiness, mostly silence. And silence, as you may be beginning to feel right now, in this moment, with your breathing slowing and your muscles softening, is not nothing. Silence is something. It is the canvas on which everything else is painted. It is the pause between notes that makes music possible. It is the dark between the stars that makes the stars visible at all. And yet, something even more remarkable waits within that silence. Something that will gently unfold over the next few hours as we drift from world to world together. Because the time it takes to reach each planet changes with the season, changes with the position of the planets in their orbits, changes with the speed of the spacecraft and the fuel it carries and the path it takes through space. It is not a fixed number. It is a living, breathing, shifting calculation that reveals, more than almost anything else, just how dynamic and alive our little corner of the universe truly is. But we will take our time with all of that. We always take our time. Now imagine you are floating, weightless, just above the atmosphere of the Earth. You can see the curvature of the planet below you, that famous blue-white arc that every astronaut who has ever reached orbit describes with the same trembling reverence. The atmosphere is so thin from up here, so heartbreakingly thin, a layer no more proportionally significant than the skin of an apple. And yet, it is everything. It is the difference between this living world and the dead silence of space. Below you, in the sunlit regions, you can see the shapes of continents. You can see the silver threads of rivers. You can see the deep blue of oceans, the vast, unhurried blue. And you realize that the oceans themselves are a kind of space, a kind of inner cosmos, mostly unexplored, mostly dark, mostly silent. And around you, in every direction, in all 360 degrees of the spherical universe that surrounds you, there is the dark. There are the stars. There is the sun, smaller than you might expect from this distance, but still blazingly bright, still the warm and patient heart of everything in this neighborhood of the galaxy. The sun, which is 400 times larger than the moon and 400 times farther away, creating one of the most beautiful coincidences in all of nature, the illusion that they are the same size in our sky. An illusion so perfect that it gives us solar eclipses, those brief, sacred moments when the moon slides precisely across the face of the sun and the corona blazes out like a crown of fire. But we are not going to the sun tonight. We are going further. We are going to every other world in this solar system, one by one, in the order they orbit outward from the sun. And each world will teach us something different, not just about the time and distance involved, but about the nature of space itself, about the strange, slow mathematics of orbital mechanics, about the counterintuitive truth that sometimes the fastest way to reach a distant world is not to aim directly at it, but to curve around something else entirely, to borrow the gravity of another planet and use it like a slingshot, like a gentle push from a cosmic hand. But first, there is something we must understand, something that changes everything. When we talk about traveling through space, we tend to think in terms of miles or kilometers. We imagine space as a kind of road and a spacecraft as a kind of very fast car, and we think that the faster you go, the sooner you arrive. And this is true in the most basic sense. But space travel is not like driving. It is not even like flying. It is something else entirely, something governed by laws that are elegant and ancient and deeply, beautifully strange. In space, everything is in motion. The Earth moves, Mars moves, Jupiter moves. They all move at different speeds, in different orbits, completing their loops around the sun in different amounts of time. And so the distance between any two planets is constantly changing. Sometimes Earth and Mars are close as they ever get, separated by only about 34 million miles of empty space. And sometimes they are as far apart as they can be, separated by more than 250 million miles, half the width of the entire inner solar system. And this matters. This matters enormously, because a spacecraft launched toward Mars when the planets are close arrives in a very different amount of time than one launched when the planets are far apart. And the fuel required, the trajectory chosen, the timing calculated to the minute and the second, all of it depends on where the planets happen to be in their eternal, graceful dance around the sun. It is, in the most literal sense, a matter of waiting for the right moment, of patience, of watching the sky and knowing when to go. And this is where the universe becomes truly mysterious and truly beautiful in a way that I want you to sit with for a moment. The trajectories we use to travel between planets are called Hohmann transfer orbits, named after a German engineer named Walter Hohmann, who calculated them in 1925, decades before any spacecraft had ever left the Earth. He sat down with his mathematics and his imagination, and he worked out the most fuel-efficient path between two orbiting bodies. And what he found was something unexpected, something almost poetic. The most efficient path is not a straight line. It is an ellipse, a gentle looping curve that starts from the orbit of the home planet, sweeps outward, and arrives at the orbit of the destination planet exactly halfway around. Like an arc, like the arm of a great invisible compass drawing a slow circle through the void. And this path takes time, more time than intuition suggests, more time than feels comfortable when you first hear the numbers. But as the night deepens and the stars wheel overhead, and your breathing grows slower and more even, the time will begin to feel different. It will begin to feel not like an obstacle, but like a gift, because what is time really out here in the dark? What does a month mean to Jupiter, which has been orbiting the sun for 4.5 billion years? What does a year mean to a star that will shine for another 5 billion more? In the scale of the universe, even the longest human life is a brief, bright flicker. And yet that flicker is enough to feel wonder, enough to look up at the stars and ask questions, enough to build machines that can cross the void between worlds. That is not a small thing. That is, perhaps, the most extraordinary thing in all the universe. So settle in now. The journey is beginning. The stars are steady above you. The earth is falling away below. And ahead of you, in the patient dark, the first of your destinations waits. Let the night carry you. Let the silence hold you. And let us go, together, to the closest world beyond our own, Mercury. The name itself is ancient. It is the name the Romans gave to their messenger god, the fleet-footed deity who carried words between worlds, between mortals and the divine. And there is something fitting about that, because Mercury, the planet, is always moving, always racing, always somewhere else by the time you look for it in the night sky. It is the closest planet to the sun, the innermost of all the worlds, the smallest of the rocky planets, a dense little sphere of iron and stone that completes its orbit around the sun in only 88 Earth days. While you are living through 3 months of your life, sleeping and waking and eating and dreaming, Mercury has already made one complete circle around the star that gives all of us life. But here is the quiet paradox that has always made Mercury fascinating. Despite being the closest planet to the sun, it is not the closest planet to Earth. Not always. In fact, Venus, the next planet out, spends more time closer to Earth than Mercury does, due to the particular geometry of their orbits. But Mercury, in a curious statistical sense, may actually be the closest planet to Earth on average, integrated over time, because of how small and fast its orbit is. It spends less time on the far side of the sun than any other planet. And yet, despite this relative proximity, traveling to Mercury is one of the most challenging journeys in the solar system. This seems backward. Surely the closest planet should be the easiest to reach? And yet the mathematics of space travel work differently. The problem with Mercury is not distance. The problem is speed. Mercury orbits the sun at nearly 107,000 miles per hour. Earth orbits at about 67,000 miles per hour. To reach Mercury, a spacecraft doesn't just need to travel inward toward the sun. It also needs to slow down enormously, to match Mercury's orbital speed, to not simply shoot past it in the dark like a pebble skipped across water. And slowing down in space requires fuel. A great deal of fuel. Imagine you are that spacecraft now. You have left Earth's orbit, and you are falling inward toward the sun. As you fall, you speed up, pulled by the sun's gravity, the way water speeds up as it flows toward a drain. By the time you approach Mercury's orbit, you are moving very, very fast. Far too fast to simply park yourself alongside Mercury and say, "Here I am." To do that, you need to fire your engines in the opposite direction, opposing your motion, burning your fuel to slow yourself down. And this costs enormously. More, in some calculations, than the fuel required to reach the outer planets. This is why the journey to Mercury has historically taken not weeks, but months, sometimes years. A Mariner 10 spacecraft, the first probe ever sent to Mercury, was launched in November of 1973, and it did not arrive at the planet until March of 1974. That is roughly 5 months of travel. But Mariner 10 did not orbit Mercury. It flew past it, using the planet's gravity to swing itself into a different orbit, allowing it to return and fly past again several more times. The first spacecraft to actually orbit Mercury was Messenger, and its journey was remarkable in its complexity and its patience. It was launched in August of 2004. It spent years weaving through the inner solar system, flying past Earth once, Venus twice, and Mercury itself 3 times, using each flyby to lose just enough speed to eventually, finally, achieve orbit around this small and ancient world. It arrived in March of 2011, nearly 7 years after launch. 7 years. Let that number settle in for a moment, not with alarm, not with impatience, but with a kind of wonder. Because in those 7 years, Messenger traveled approximately 7.5 billion kilometers through the solar system. It flew a winding, looping, patient path through the inner solar system, borrowing gravity here and losing speed there, guided by equations calculated with extraordinary precision by engineers who understood that the straightest path is not always the swiftest one. And when it arrived, when it finally slipped into orbit around Mercury, for the first time in the history of human exploration, the world it found was ancient and scarred and surprisingly beautiful. Mercury's surface is a record of everything the solar system has thrown at it over 4.5 billion years. Every crater, every basin, every long, winding cliff called a rupes is a scar from an impact, a memory of a collision in the early chaos of planetary formation. The planet has almost no atmosphere to erode these marks, to sand them smooth with wind and weather. What happened 4 billion years ago is still visible on the surface. Time has barely touched it. And the temperatures. The temperatures on Mercury are among the most extreme in the solar system, and not for the reason most people assume. Because Mercury has almost no atmosphere, it cannot hold heat the way Earth does. In the places where the sun shines, temperatures soar to nearly 430 degrees Celsius, hot enough to melt lead. But on the side facing away from the sun, temperatures plunge to minus 180 degrees Celsius, cold enough to freeze nitrogen. And somehow, impossibly, deep in certain craters near Mercury's poles, places where the sun never shines, where the geometry of the planet's tilt keeps them in perpetual shadow, there is water ice. Ancient, cold, preserved against all expectation by the very darkness that surrounds it. Water ice on the closest planet to the sun. The universe never stops surprising. Imagine floating above Mercury now, in the silence of its orbit, watching the sun rise over its cratered surface. Because Mercury rotates so slowly and orbits so quickly, a solar day on Mercury, the time from one sunrise to the next, actually lasts longer than a Mercurian year. The planet completes 2 full orbits around the sun in the time it takes to rotate 3 times on its axis, a gravitational resonance with the sun that locked it into this strange rhythm billions of years ago. So there is a place on Mercury's surface where you can stand and watch the sun rise, move through the sky, slow, stop, and then reverse, move backward, set in the direction it rose from, and then rise again, before finally setting in the west after an extraordinarily long day. The physics of the universe, even here in our quiet corner of the galaxy, is full of wonders that make the word strange feel entirely inadequate. And yet there is a stillness to Mercury, a quietness. It has no moon, no rings, no weather, no seasons in the way we understand them. Just the slow rotation, the relentless sun, the ancient craters, and the silence. A silence so complete that it makes this moment right now feel loud by comparison. But there is more, always more, and as we leave Mercury behind and let it continue its swift, solitary orbit around the sun, we turn our gaze outward toward the next world. And the next world is one of the most beautiful and most terrible places in the solar system. We are going to Venus, and the journey there will teach us something new about the nature of distance, and time, and the deceptive familiarity of a world that looks from a distance, like home. Venus, if you have ever seen a bright, steady light low in the western sky just after sunset, or low in the eastern sky just before dawn, and wondered what it was almost certainly Venus. It is the brightest object in the night sky after the moon, bright enough to cast a shadow on a dark night, bright enough that it has sometimes been mistaken for an aircraft, or a star, or something more mysterious. It is neither near nor far, as these things go in the solar system. It is the second planet from the sun, and it is our nearest neighbor, the planet that approaches closest to Earth during its orbital dance. At its nearest point, Venus is only about 38 million miles from Earth, closer than any other planet ever gets. At its farthest, it is about 160 million miles away, on the opposite side of the sun. And traveling to Venus, in terms of the time required, is among the more achievable journeys of the solar system. A spacecraft following an efficient Hohmann transfer orbit can reach Venus in roughly 3 to 5 months, depending on the timing of the launch window. The Venera spacecraft sent by the Soviet Union in the 1960s, 70s, and 80s made the trip in periods ranging from about 3 to 4 months. NASA's Magellan spacecraft, launched in 1989, took about 15 months, though it took a longer, less direct path. The average, for a reasonably efficient trajectory, is somewhere around 4 months of travel. 4 months of floating in the dark, engines mostly silent, the sun growing slightly larger and brighter ahead of you, the blue marble of Earth shrinking away behind. Now, imagine arriving. Imagine your spacecraft slipping into orbit around Venus, and the first thing you see is not a surface. It is a ceiling. A thick, impenetrable, utterly opaque ceiling of pale yellowish-white clouds, stretching from horizon to horizon in every direction, completely hiding the world below. Venus is wrapped in clouds. Clouds of sulfuric acid, suspended in an atmosphere of carbon dioxide that is 92 times denser than Earth's atmosphere. Standing on the surface of Venus would feel, in terms of pressure, like standing 900 meters below the surface of the ocean. The weight of the air would be immense, pressing in on you from every direction. And the temperature. Venus holds the record for the hottest surface of any planet in the solar system, including Mercury. Even though it is nearly twice as far from the Sun, its surface averages about 465 degrees Celsius, hot enough to melt lead, hot enough to incinerate any organic material within moments. This is the greenhouse effect taken to its ultimate, terrifying conclusion. The thick carbon dioxide atmosphere traps the Sun's heat so completely that the temperature on Venus barely changes between day and night. Between the sunlit hemisphere and the one facing away from the Sun, there is no relief, no cool side, no respite. The entire planet is an oven. And yet, Venus is sometimes called Earth's twin. It is almost exactly the same size as Earth. Its mass is about 82% of Earth's. Its gravity is about 90% of Earth's. If you could stand on Venus, you would feel only slightly lighter than you do at home. Its composition of rock and iron is similar to Earth's. In many ways, it is the planet most like Earth in the solar system. But the conditions diverged somewhere in their shared history. Earth developed oceans, life, a carbon cycle that keeps carbon dioxide locked in rocks and living things instead of the atmosphere. Venus did not. Perhaps its oceans evaporated in a runaway greenhouse process long ago. Perhaps it never had them. We do not know for certain. There is a quiet sadness in contemplating Venus, in considering what it might have been, what it might still have been if its story had unfolded differently. And there is a quiet wisdom in that sadness, a reminder that the conditions for life, for blue skies and liquid water and breathable air, are not guaranteed. They are earned, somehow, through a combination of location and composition, and chance that we are only beginning to understand. But there is also wonder. Because Venus rotates backward, if you were standing on Venus and could somehow see the Sun through those thick clouds, it would rise in the west and set in the east. Venus rotates on its axis in the opposite direction from Earth, from Mars, from most of the planets. And it rotates extraordinarily slowly. A day on Venus, one full rotation, takes 243 Earth days, which is actually longer than a Venusian year, which takes only 225 Earth days. A day longer than a year. Venus moves through its orbit faster than it spins. It is a world in no hurry to reveal its face to the universe. And high in the Venusian clouds, in that thick swirling, perpetually moving layer of sulfuric acid droplets, temperatures and pressures become almost Earth-like. Around 50 kilometers above the surface, the pressure is roughly 1 Earth atmosphere. The temperature is between 0 and 50 degrees Celsius. It is warm, but survivable. It is the most Earth-like environment in the solar system outside of Earth itself. Some scientists have wondered, quietly and carefully, whether something might live there. Not on the surface, which is hellish, but in the clouds, floating in the clouds. In 2020, a paper was published announcing the potential detection of phosphine gas in the Venusian atmosphere. Phosphine on Earth is produced almost exclusively by living organisms or by industrial processes. Its presence in Venus's atmosphere was unexpected, puzzling, and deeply intriguing. The results have been debated since. The detection may have been an artifact of the data analysis. The phosphine may have a non-biological explanation. The mystery is not resolved, but the question lingers, soft and persistent, like a light in the clouds. Could there be something alive in the skies of Venus? We drift away from that question now, carrying it with us, letting it float alongside us like a companion as we leave Venus's thick, golden clouds behind and turn our spacecraft outward again. The sun, still bright, begins to shrink very slightly as we add distance. And ahead of us, in the direction the Earth cannot be seen from here, a reddish point of light grows slowly brighter. We are going to the planet that has captured human imagination more than any other. The planet we have dreamed about visiting for centuries. The planet that, in our own time, we are actually beginning to plan journeys to. We are going to Mars, and the journey is longer than most people think, even though Mars feels somehow familiar, somehow close, somehow almost within reach. It is not. Or rather it is, but only just barely, and only if you wait for the right moment, and only if you accept that space does not hurry, that it cannot be rushed, that the patience required to cross even this relatively modest distance is a kind of discipline that changes how you think about time itself. Mars, red, cold, ancient, and somehow calling. It has called to human beings for as long as we have looked up at the night sky and seen it there, that faintly reddish star that moves among the fixed stars with a stately, unhurried motion. The ancient Egyptians called it Hor-Desher, the red one. The Babylonians called it Nergal, their god of war and death. The Greeks named it Eris, the Romans Mars, the red that caused so many civilizations to associate it with blood and conflict is iron oxide, rust, the same rust that forms on old iron pipes left in the rain. Mars is a rusty planet. It is rusting in the dark. And yet there is nothing dark about Mars in the imagination. For more than a century, it has been the planet of possibility, the planet of what might be, the planet where science fiction set its greatest stories and its boldest visions, where H.G. Wells placed his invaders, where Edgar Rice Burroughs set his adventures, where scientists and dreamers alike have pointed and said, perhaps there, perhaps that one. How long does it actually take to get there? The answer varies more than people realize because of the nature of planetary orbits. Earth and Mars orbit the Sun at different speeds and at different distances, completing their loops in different amounts of time. Earth takes 365 days. Mars takes roughly 687 Earth days. And this means that the distance between them changes constantly, in a slow rhythmic pattern that repeats approximately every 26 months. Every 26 months, Earth and Mars align in a configuration called opposition, when they are on the same side of the Sun and relatively close to each other. These are the windows, the moments, the carefully watched and long anticipated opportunities for launching spacecraft toward Mars. And even then, the spacecraft doesn't travel in a straight line. It travels in an arc, a Hohmann transfer ellipse, swooping outward from Earth's orbit and curving to meet Mars's orbit on the other side. The typical travel time for this kind of trajectory is somewhere between 6 and 9 months. 6 to 9 months of floating through the interplanetary medium, through the thin soup of solar wind and magnetic fields and occasional dust that fills the space between the planets. 6 to 9 months of weightlessness, of watching the stars through small portholes, of Earth growing smaller and Mars growing larger in the dark. The first successful mission to Mars, NASA's Mariner 4, launched in November of 1964 and arrived at Mars in July of 1965, was approximately 7.5 months of travel, and when it arrived, it did something no spacecraft had ever done before. It flew past Mars and took photographs. 22 photographs, grainy and low resolution by modern standards, but showing for the first time in human history the actual surface of another planet up close. What it showed was craters, ancient, eroded craters like the moon. Mars, in those first images, looked dead, cold and dead and ancient, with no sign of the canals that some astronomers had thought they saw through their telescopes in the 19th century. No canals, no cities, no civilization. Just craters and dust and silence. But Mars has not been silent since. We have sent dozens of missions to Mars. Orbiters, landers, rovers. Rovers that crawl slowly across the surface on 6 wheels, analyzing rocks, drilling into soil, taking panoramic photographs that show landscapes so eerily Earth-like and yet so obviously alien that they produce a kind of cognitive vertigo in anyone who looks at them long enough. And what Mars has revealed over these decades of exploration is a world with a history far richer and stranger than those first cratered photographs suggested. Mars has the tallest volcano in the solar system. Olympus Mons is approximately 22 kilometers high, nearly 3 times the height of Mount Everest, rising from the surrounding plains in a great, gentle dome so wide that if you stood at its summit, the edges of the volcano would be over the horizon. You would not know you were standing on a volcano at all. You would simply feel the ground rising slowly in every direction while the horizon curved away from you. Mars has the longest, deepest canyon system in the solar system. Valles Marineris stretches for nearly 4,000 kilometers along the equatorial region of the planet, a canyon so vast that the Grand Canyon could fit inside one of its smaller tributaries. It is not a river canyon. It is a tectonic scar, a place where the crust of Mars cracked and pulled apart billions of years ago, leaving this enormous gash in the red surface that has been silent and still ever since. And Mars, crucially, beautifully, has water. Not liquid water on the surface, not now, not under the current conditions of thin atmosphere and bitter cold, but water ice at the poles. Water ice buried beneath the surface in vast permafrost layers. Ancient dried riverbeds that trace the paths of rivers that once flowed across the surface billions of years ago, when Mars had a thicker atmosphere and warmer temperatures and liquid water pooling in its basins and flowing to the sea. There was a sea. Mars once had an ocean in its northern hemisphere. It is called the Vastus Borealis, the vast northern plain, and the evidence suggests that it was once filled with water, a shallow northern ocean beneath the sky with enough air pressure to allow rain to fall and rivers to flow and life, perhaps, to begin. What happened to all of it? Mars lost its magnetic field long ago, billions of years in the past. Without that magnetic shield, the solar wind, a constant stream of charged particles that flows outward from the sun, began to strip away the Martian atmosphere. Over billions of years, the air thinned, the temperatures dropped, the oceans evaporated or froze, the rivers stopped flowing, the rain stopped falling, and Mars became what it is today, cold and dry and silent under a pinkish sky. But the subsurface remains. And beneath the southern polar ice cap, scientists believe they have detected a reservoir of liquid water, kept liquid by the pressure and the heat from below, deep in the dark beneath the ice. There is still liquid water on Mars, hidden, ancient, cold, and dark. But there, now imagine you have made the journey. You have floated through 7 months of interplanetary space, watching Mars grow from a point of light to a disk to a world filling your window. You have entered orbit, and now you look down at the ochre and rust-red surface, at the white flash of ice at the pole, at the dark scar of Valles Marineris running across the equator like a wound. You see dust storms brewing over the plains, vast, swirling clouds of fine red dust that can sometimes grow large enough to blanket the entire planet. And you feel, above everything, a sense of recognition. Mars looks familiar, not like Earth, exactly. Not like home, but like somewhere a human being could stand and understand. The horizon is the right kind of distance. The sky, though pink and thin, is still a sky. The mountains are mountains. The plains are plains. And somewhere down there, somewhere in the layered red rocks that line the walls of ancient lake beds, somewhere in the chemistry of the cold, dry soil, the answer to one of the great questions of science may be waiting. Was there ever life on Mars? The question hangs in the air of this quiet night, like a note held at the end of a piece of music, not resolved, not abandoned, just suspended, patient, waiting for the next note to come. We will leave it suspended. We leave Mars behind, now, letting it shrink in the rear view of our imagination as we accelerate outward. outward toward the cold and the dark and the grandeur of the outer solar system. Because what lies beyond Mars is not simply more planets. What lies beyond Mars is a different kind of solar system entirely. Larger, colder, more majestic in a way that is hard to describe without the word vast, and even that word, as we have seen, begins to feel inadequate. But first, we must cross the belt, the asteroid belt. That wide, quiet band of rocky debris, relics of the solar system's formation, suspended between the inner and outer solar system like a scattered mote. And beyond it, growing slowly brighter as we approach, the largest planet in our solar system waits in its endless orbit, patient as a god. We are going to Jupiter. And the journey changes everything. Jupiter. Say the name slowly and let it settle. Jupiter. There is weight in that name, and it is appropriate, because Jupiter is the weightiest thing in the solar system that is not a star. It is a planet so enormous that all of the other planets combined, Mercury and Venus and Earth and Mars, and Saturn and Uranus and Neptune, and all the moons, and all the asteroids, and all the comets, all of it together could fit inside Jupiter with room to spare. It is not simply large. It is an entirely different category of large. Jupiter's equatorial diameter is approximately 142,000 kilometers. Earth's diameter is about 12,700 kilometers. That means you could fit 11 Earths side by side across Jupiter's face, or 1,300 Earths inside Jupiter's volume. It is a number that the human mind can hear without truly absorbing. It is the kind of number that requires a different kind of thinking, a slower kind, a more patient kind, the kind of thinking that this quiet night is beginning to cultivate. And Jupiter is not made of rock like the inner planets. It is made mostly of hydrogen and helium. It is, in essence, a failed star, a world that accumulated so much mass during the formation of the solar system that it became something between a planet and a sun, but with just 5% of the mass needed to ignite nuclear fusion in its core, just 5% short of becoming a second sun. If Jupiter had been a little larger, our solar system would have been a binary star system. The nights on Earth, if Earth had formed at all under such conditions, would have had 2 suns, 2 sources of light, 2 shadows for every object on the ground. But Jupiter did not quite make it, and so it hangs there, enormous and patient, the lord of the outer solar system, its great striped face marked by the most famous storm in the solar system, the Great Red Spot, a storm larger than the entire Earth, a spinning, oval vortex of wind and cloud that has been raging continuously for at least 350 years, possibly much longer. A storm that has been watched by every telescope turned toward Jupiter since the 17th century. That has been photographed by every spacecraft that has passed through the outer solar system, that has been studied, modeled, speculated about, and wondered at, and that shows no signs of disappearing. It is not a gentle storm. Winds at its edges reach over 400 kilometers per hour. Clouds tower 40 kilometers above the surrounding cloud layers. The colors, those deep russets and oranges and creams, are thought to come from complex organic molecules created by the sun's ultraviolet light, interacting with Jupiter's atmosphere, including possibly phosphine, the same compound whose detection at Venus caused such recent excitement. And now imagine the journey to get here. The distance from Earth to Jupiter varies considerably depending on where both planets are in their orbits. At closest approach, Jupiter is about 590 million kilometers from Earth. At its farthest, it is nearly 900 million kilometers away. And an efficient spacecraft trajectory, launched at the right window, takes somewhere between 1 and 2 years to complete. 1 to 2 years. The first spacecraft to reach Jupiter was Pioneer 10, launched in March of 1972. It arrived at Jupiter in December of 1973, after a journey of about 21 months. Pioneer 10 had to cross the asteroid belt, a passage that scientists of the time were genuinely uncertain about. The asteroid belt, in science fiction and public imagination, is often depicted as a dense, dangerous field of tumbling rocks through which a spacecraft must carefully navigate. In reality, the asteroid belt is almost entirely empty space. The rocks within it are separated by vast distances, and Pioneer 10 crossed it without incident. On its way to Jupiter, Pioneer 10 encountered something else as well, something quiet and cold and vast, the true scale of the outer solar system. Because beyond Mars, beyond the asteroid belt, the distances between things grow differently. In the inner solar system, planetary distances are measured in tens or hundreds of millions of kilometers. In the outer solar system, they are measured in hundreds of millions, then billions. The scale shifts. Space grows emptier. The sun, visible from Earth as a blindingly bright disk, becomes, from Jupiter's distance, a very bright star. Still the brightest thing in the sky by far. Still the warm heart of the solar system, but a star, not a sun. A point of brilliant light in a black sky. Imagine floating in space at Jupiter's distance from the sun and holding up your hand. The sun would appear about 5 times smaller than it appears from Earth. Its warmth would be 25 times less intense. It would still be day, in a sense, but a colder, dimmer kind of day, full of long shadows and subdued colors. And yet Jupiter itself would be astonishing. From close orbit, Jupiter fills the sky in a way that no planet does from Earth's surface. That vast striped face, those bands of cloud in cream and orange and brown, the swirling, turbulent zones and belts, the shadow of a moon crossing the disk like a tiny, perfect circle. It would be overwhelming in the best sense. The kind of overwhelming that silences thought, that empties the mind of everything except the simple, wordless experience of being there, of witnessing something so enormous and so beautiful that ordinary language begins to fail. And Jupiter's moons. Jupiter has 95 known moons. Some of them are tiny, irregular chips of rock captured long ago by Jupiter's gravity, too small and distant to be more than points of light. But the 4 largest, the Galilean moons discovered by Galileo Galilei in 1610, are worlds in their own right. Io is the most volcanically active body in the solar system, covered in sulfur volcanoes that erupt in plumes hundreds of kilometers into space, constantly reshaping the surface in oranges and yellows and whites so vivid they look painted. It is the most tormented world in the solar system, squeezed and stretched by Jupiter's immense gravity in a process called tidal heating that keeps its interior permanently molten. Europa is perhaps the most exciting. Beneath its smooth, cracked shell of water ice, scientists believe there is a global ocean of liquid salt water, kept liquid by that same tidal heating. A warm ocean in the dark beneath the ice. And where there is liquid water, warm water, chemistry, there is the possibility of life. Europa's hidden ocean may be one of the best places in the solar system to look for biology beyond Earth. Ganymede is the largest moon in the solar system, larger than the planet Mercury, the only moon known to have its own magnetic field. It too may have an ocean beneath its icy surface. Callisto is ancient and cratered, a testament to 4 billion years of cosmic bombardment. Its surface barely changed since the early solar system, a record of impacts stretching back to the beginning. 4 worlds, each one worthy of its own dedicated mission, its own dedicated wonder, its own quiet night of contemplation. And here, from Jupiter's orbit, we pause for a moment and look back. Look back at the inner solar system, now. Mercury, Venus, Earth, Mars, all of them are invisible to the naked eye from here. They are too far, too small, too dim. Even Earth, our beautiful blue marble, from Jupiter's distance appears as little more than a faint blue point of light, barely distinguishable from stars. It is the pale blue dot that Carl Sagan spoke of when the Voyager 1 spacecraft turned its camera backward and took a photograph from the edge of the solar system. From Jupiter's distance, that photograph would show an even smaller, fainter dot. There is something profound in that smallness, There is something deeply calming in understanding that everything you have ever known, every person, every city, every ocean, every mountain, every dream and fear and hope, exists on a point of light that can barely be distinguished from a star when viewed from the orbit of Jupiter. Not frightening, calming, because if all of that, all of human history and experience and meaning, can exist on a speck, then the speck is not diminished. The speck is miraculous. And yet, as we turn our gaze outward again, there is still so much further to go. Saturn waits ahead of us, patient and golden and ringed. And the journey there will carry us further into the silence than we have been yet. Saturn, if there is one image that most people carry in their minds when they think of the solar system, when they think of planets in space and the wonder of what lies beyond our world, it is often Saturn. That pale golden disk, impossibly ringed, hovering in a black sky like something from a dream. A planet so beautiful that early astronomers who first saw it through their telescopes thought they might be hallucinating. When Galileo first observed Saturn through his primitive telescope in 1610, he could not make out what he was seeing clearly. The rings appeared to him as two companions flanking the planet on either side. He thought Saturn might have ears or wings. It was only decades later, when telescopes improved, that the rings were recognized for what they truly are. And what they are is one of the most extraordinary structures in the natural world. Saturn's rings extend outward from the planet's equator for nearly 300,000 kilometers, more than 75 times the distance from Earth to the Moon. They are almost unimaginably wide in their radial extent. And yet, they are extraordinarily thin. The main rings are, in most places, less than a kilometer thick. 1 kilometer thick, spread across 300,000 kilometers of width. If you were to scale the rings to a sheet of paper, that paper would need to be more than 3 kilometers in diameter. The rings are made of ice and rock, ranging in size from tiny grains to chunks several meters across, all in orbit around Saturn, all moving at slightly different speeds depending on their distance from the planet. They glitter in the sunlight with a cold, crystalline beauty that no photograph has ever fully captured. Where did they come from? The answer is still debated. One possibility is that a moon of Saturn, perhaps a moon the size of our own moon, wandered too close to Saturn long ago and was torn apart by tidal forces, its material spreading out into the ring plane. Another possibility is that they are remnants from the early solar system, material that never coalesced into a moon. A third possibility is that they formed relatively recently, in the last 100 million years or so, cosmically speaking, a blink of an eye. What is known is that the rings are not permanent. They are slowly spiraling inward, raining down onto Saturn's atmosphere, a process called ring rain, and if nothing changes, they will be gone within 100 million years. We live in a special time, a brief cosmic window, when Saturn wears its extraordinary rings, and the journey to reach them? Saturn is, on average, about 1,200,000,000 kilometers from the Sun. Earth is about 150 million kilometers from the Sun. The distance between Earth and Saturn, depending on orbital positions, ranges from about 1.2 billion to 1.7 billion kilometers. An efficient spacecraft trajectory typically takes 3 to 4 years to reach Saturn. 3 to 4 years. And yet, in all that time, in all that quiet dark between Earth and Saturn, there is not nothing. There is the asteroid belt, crossed again. There is the slow, gradual dimming of the Sun as distance accumulates. There is Jupiter, either in the way or offering a gravitational assist, depending on the orbital geometry at the time of launch. And there is the growing realization, deep in the bones, that space is genuinely, terrifyingly, beautifully large. The most famous mission to Saturn is Cassini. Launched in October of 1997, Cassini arrived at Saturn in July of 2004, after a journey of almost 7 years. It used gravity assists from Venus, Earth, and Jupiter to build the speed it needed to cross the vast distance to the outer solar system. And when it arrived, it began one of the most remarkable scientific missions in human history. For 13 years, Cassini orbited Saturn. It made 293 orbits. It studied the rings in extraordinary detail. It discovered active geysers of water vapor and ice shooting from the south pole of a small moon called Enceladus. Geysers fed by a global subsurface ocean beneath the ice, an ocean that Cassini flew through and sampled directly. It found that this ocean contains hydrogen, the kind produced by hot water reacting with rock on the ocean floor, the same kind of process that, on Earth, supports entire ecosystems of life in the deepest, darkest ocean trenches. Enceladus may have the conditions for life. A moon of Saturn. Not Earth, not Mars. A small, icy moon orbiting a gas giant in the cold outer solar system. And its hidden ocean might be alive. The universe has ways of making you rethink everything. Cassini also studied Titan, Saturn's largest moon, the only moon in the solar system with a thick atmosphere. Titan's atmosphere is mostly nitrogen, like Earth's, but it is cold, extraordinarily cold. Minus 179 degrees Celsius, too cold for liquid water. Instead, Titan has lakes and rivers and seas of liquid methane and ethane. It has rain, but it rains methane. It has dunes, but they are dunes of organic material, complex carbon compounds that drift across the landscape in the dim light of a very distant sun. Cassini carried a probe called Huygens, which was released to fall through Titan's atmosphere in January of 2005. Huygens parachuted down through the orange haze, transmitting data and images for 2 hours and 27 minutes as it descended, and for a little while after it landed on the surface. It landed on a surface that looked like a riverbed, covered in smooth, rounded pebbles of water ice. It landed on the shore of what appeared to be a dried-up sea, a sea that had once been full and was now mostly drained, a landscape shaped by flowing methane, in the same way that Earth's landscapes are shaped by flowing water. A world of methane rivers and nitrogen winds and organic dunes and orange skies, orbiting a ringed giant 4.5 billion kilometers from the sun. And somehow it is beautiful. In an alien, cold, utterly different way, it is beautiful. We linger for a moment in Saturn's orbit, letting the golden planet and its rings fill the imagination, letting the image settle like a painting on the wall of the mind. The rings catch the distant sunlight and scatter it in complex patterns of light and shadow. A moon crosses the disk. Another casts its shadow on the rings. The belts and bands of Saturn's atmosphere, subtler than Jupiter's, drift in slow patterns. And then we move on, because there is still so much further to go. The outer solar system opens up ahead of us, wider and colder and more remote. And the next planet, the one we are going to next, is a world that was discovered not by sight, but by mathematics. A planet predicted into existence by the logic of celestial mechanics before anyone had seen it. We are going to Uranus, and the time it will take to get there will be longer than any time we have considered yet, long enough to make the journeys to the inner planets feel like a short drive on a Sunday afternoon. Uranus, it is a strange name, and it leads to jokes among people first encountering it. But the name is ancient, the name of the Greek god of the sky, Uranus, the primordial deity who was the heavens themselves. And there is something fitting in naming this distant, sky-colored world for the sky, because Uranus is blue. Not the deep cobalt blue of Earth's oceans, but a soft, pale, almost luminescent blue-green, the color of shallow tropical water in a sunlit bay, the color of a swimming pool on a clear day. This color comes from methane in its upper atmosphere, which absorbs red light and reflects blue-green light back into space. And Uranus is far. At its average distance from the Sun, Uranus orbits at about 2.9 billion kilometers. Earth, recall, orbits at 150 million kilometers. The ratio is almost 20 to 1. Uranus is nearly 20 times farther from the Sun than we are. From Uranus, the Sun appears as a very bright star, perhaps 300 times fainter than we see from Earth. Still clearly the sun, still the brightest object in the sky by far, but small enough that you could cover it with your extended thumb. A brilliant point of light in a black sky, casting shadows, but no warmth worth speaking of. The average temperature of Uranus's cloud tops is minus 214 degrees Celsius. Cold beyond imagination. And quiet. Uranus is, in many ways, the quietest of the giant planets. It emits very little internal heat, unlike Jupiter and Saturn and Neptune, which all radiate more heat than they receive from the sun. Uranus seems to have no significant internal heat source, or if it does, that heat is somehow trapped deep inside, unable to escape. It is, in this sense, still mysterious. What is not mysterious is Uranus's extraordinary axial tilt. Every planet in the solar system is tilted slightly on its axis, the angle between the axis of rotation and the plane of the orbit. Earth's tilt is 23.5 degrees, which gives us our seasons. Mars has a similar tilt. Saturn and Jupiter are somewhat tilted, but Uranus is tilted 97.8 degrees. That means Uranus orbits the Sun essentially on its side. Its north and south poles point almost directly toward and away from the Sun as it moves through its orbit. This leads to the most extreme seasons in the solar system. During its summer, Uranus's north pole points almost directly at the Sun, bathing the entire northern hemisphere in continuous sunlight for about 21 Earth years, while the southern hemisphere languishes in complete darkness. Then, as Uranus continues its slow 84-year orbit of the Sun, the seasons gradually shift, until the South Pole is pointing toward the Sun for another 21 years. Imagine a place where summer lasts 21 years, and winter lasts 21 years, and during that winter, the Sun never rises at all. Such a place exists. It orbits our Sun. It is real. The only spacecraft to have visited Uranus is Voyager 2, which conducted a flyby in January of 1986. It had been launched in August of 1977, almost 9.5 years earlier. 9.5 years of quiet, patient travel through the outer solar system, growing farther from Earth with every second, the Sun shrinking behind it. Voyager 2 revealed that Uranus has a system of thin, dark rings, discovered earlier by astronomers observing the planet blocking background stars. It also revealed 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope: Miranda, Ariel, Umbriel, Titania, Oberon. These moons have their own strange characters. Miranda, the smallest of the major moons, has a canyon system 10 times deeper than the Grand Canyon. Its varied terrain suggests a violent history, possibly multiple collisions and reassembly. Uranus has not been revisited since Voyager 2's brief flyby. It remains, in many ways, the least understood of the giant planets, a pale blue mystery at the edge of the known solar system. A journey to Uranus today, on the most efficient trajectory, would take approximately 9 to 13 years. 9 to 13 years of travel. That is a significant portion of a human career. A child born the year such a mission launches would be in high school by the time it arrived. And yet, it would be worth it. It would be worth every year. Because Uranus, for all its quietness and mystery, is a world that almost certainly holds secrets we have not yet asked the right questions to uncover. Now imagine continuing outward from Uranus. The Sun is just a star now, a very bright star, the dominant feature of the sky, but not a disk, not a warmth. Just light. Cold, ancient light that takes 4 hours to travel from the Sun to where you are. 4 hours. On Earth, light from the Sun takes only 8 minutes to reach us. At Uranus, it takes 2 hours and 40 minutes. At the orbit of our next destination, it takes over 4 hours. We are going to Neptune. Neptune, the 8th and farthest planet from the Sun, the outermost of the great planets, the edge of the planetary solar system. Neptune was discovered in 1846, not by looking, but by calculating. Two mathematicians, the Englishman John Couch Adams and the Frenchman Urbain Le Verrier, independently analyzed irregularities in the orbit of Uranus and concluded that they must be caused by the gravitational pull of an undiscovered planet. They calculated where that planet must be, and when astronomers pointed their telescopes at that spot in the sky, there it was. Mathematics, seeing what eyes could not. Neptune is slightly smaller than Uranus, but it is denser. Its blue color is deeper, a richer, more vivid blue. Interestingly, Neptune has a more dynamic atmosphere than Uranus, with strong winds, the fastest in the solar system, reaching speeds of over 2,000 kilometers per hour. Great white clouds streak across its face. Dark storms form and dissipate. The great dark spot, observed by Voyager 2 when it flew past in 1989, has since disappeared, replaced by new features that were not there when the spacecraft looked. Neptune is alive, atmospherically. For a world so cold, so distant, so far from the sun's energizing warmth, it has enormous weather energy. This energy comes from within, from the slow release of heat generated by the planet's formation billions of years ago, still bleeding slowly outward through the cold atmosphere. Voyager 2, after completing its flyby of Uranus, continued outward to Neptune, arriving in August of 1989, 12 years after its launch. The journey from Uranus to Neptune alone had taken approximately 3.5 years. The total journey from Earth to Neptune was 12 years. 12 years. There have been no other spacecraft to Neptune since Voyager 2's brief flyby. No orbiter, no probe dropped into the atmosphere, no lander on any of its moons. Neptune remains almost entirely unexplored, and its largest moon, Triton, is one of the strangest objects in the solar system. Triton orbits Neptune backward, in the opposite direction of Neptune's rotation, which is impossible for a moon that formed from the same material as its planet. Triton was captured, long ago, from the outer solar system. It is a world that was once free, orbiting the sun on its own path, until Neptune's gravity caught it and pulled it in. And it is slowly spiraling inward. In approximately 3.5 billion years, Triton will cross a threshold called the Roche limit and be torn apart by Neptune's gravity, its material scattered into a ring that will circle Neptune for a time before slowly raining down onto the planet. Everything in the solar system, given enough time, is in motion. Everything changes. Everything ends and becomes something else. But for now, for this moment in geological time, Triton is still intact, still orbiting its adopted planet, still covered in its strange pink and white surface of frozen nitrogen with geysers that erupt dark streaks across the ice. It is cold there beyond any meaningful comparison. 38 degrees above absolute zero, the coldest measured surface temperature of any natural object in the solar system. And from Triton's surface you could look up and see Neptune hanging in the black sky, huge and blue and impossibly beautiful, its cloud features visible to the naked eye, its rings a faint, barely there shimmer. And beyond Neptune, beyond the entire planetary solar system, the true outer solar system begins. A region that most people have never heard of. A region that Voyager 1 crossed and is still crossing. A region so vast, it makes everything we have discussed tonight seem like an afternoon walk. But that, the truly deep outer solar system, the heliopause, the Oort cloud, the edge of the sun's domain, that is for a later, quieter moment. For now, let us hover here at Neptune's orbit, at the edge of the planetary solar system, and let the silence settle. Neptune is approximately 4.5 billion kilometers from the sun. It takes sunlight 6 hours to make that journey. The planet completes one orbit of the sun every 164.8 years. It has orbited the sun only once since it was discovered in 1846. Only once. We have been watching it for 1 year of its life. 1 year. and it was already 4.5 billion years old when we found it. These are the numbers that make sleep seem natural, that make the racing thoughts of the day grow still and heavy, that remind you how small the urgent things are, how patient the universe is, how little hurry there truly is in the grand scheme of a cosmos that measures its existence in billions. Breathe. Let the dark settle around you. There is more to come. We have reached the edge of something. Not the edge of the solar system, not yet, but the edge of the planetary solar system, the region we think of when we think of our sun's family. Behind us now, in the direction of the inner warmth, all 8 planets orbit their quiet orbits, each one a world with its own story, its own silence, its own impossible distances. But ahead of us, ahead and around and above and below, the solar system continues. Not as planets, but as something else. Something slower, colder, and more mysterious. Between Neptune and the next nearest star, there is not empty space. There is something. Many things. A vast, slow-moving population of icy bodies, some the size of mountains, some larger, all in distant orbits around the sun, all moving so slowly that a single orbit might take millions of years. The first of these regions is called the Kuiper Belt. It extends from Neptune's orbit outward to about 50 times the Earth-Sun distance, a broad, flat disk of icy objects left over from the formation of the solar system. It is home to Pluto, which was once considered the 9th planet and is now classified as a dwarf planet. The largest known Kuiper Belt object at the time of its reclassification, Pluto is smaller than Earth's moon. Its surface is covered in frozen nitrogen, with mountains of water ice that rise 3,000 meters above the plains. In 2015, NASA's New Horizons spacecraft flew past Pluto, 9.5 years after its launch, traveling at more than 50,000 kilometers per hour, the fastest spacecraft ever launched. And what it showed was a world of extraordinary beauty. A vast plain called Tombaugh Regio, shaped roughly like a heart, so large and bright that it is visible even in the low-resolution images from Earth. This heart-shaped region is a nitrogen glacier, slowly flowing, slowly moving in patterns so slow that a single convection cell circulates over millions of years. Blue skies above a red and white surface. A haze of organic particles in the atmosphere, giving Pluto sunsets of impossible beauty. And beyond Pluto, the Kuiper Belt extends further still, filled with more objects, more worlds not yet visited, not yet named, slowly orbiting in the cold. Beyond even the Kuiper Belt lies a theoretical region called the scattered disk, where objects have been pushed onto highly elliptical orbits by interactions with Neptune's gravity. And beyond that, so far beyond that it boggles the imagination, lies the Oort cloud. The Oort cloud is not really a cloud. It is a vast spherical shell of icy bodies surrounding the entire solar system, extending from roughly 2,000 to 100,000 times the Earth-Sun distance. It is so far from the Sun that the Sun appears to the objects within it as nothing more than a very bright star. Objects in the outer Oort cloud are only very loosely bound to the Sun's gravity, and they are occasionally disturbed by passing stars or galactic tidal forces and sent plunging inward on long, slow journeys toward the inner solar system. These are the long-period comets, the ones with orbits that take thousands or millions of years to complete. The comets we see streaking across Earth's sky, those brief, bright visitors with their trailing tails of gas and dust, are most likely visitors from the Oort cloud, travelers that left their home in the far dark, tens of thousands of years ago, and are only now, at the end of their long inward fall, passing through the inner solar system for the first time. Perhaps for the only time. They may never return. The nearest star to the Sun, Proxima Centauri, is approximately 4.2 light-years away. 1 light-year is the distance light travels in a year, approximately 9.5 trillion kilometers. 4.2 light-years is about 40 trillion kilometers. And the outer edge of the Oort cloud may extend roughly 1 to 2 light-years from the Sun. which means that the sun's gravitational domain, the region where objects are loosely bound to the sun, may extend almost halfway to the nearest star. Our solar system is not a small thing. Even the space between stars is not truly empty. Now imagine a spacecraft launched today, right now, heading in the direction of Proxima Centauri at the fastest speed ever achieved by a human-made object. The fastest spacecraft ever launched from Earth, the New Horizons probe, travels at about 58,000 kilometers per hour. At that speed, it would take approximately 80,000 years to reach Proxima Centauri. 80,000 years. When the ancestors of every person alive today were living in small bands on the African savanna, drawing pictures on cave walls, learning to make fire and tools and language, that spacecraft would have been just leaving. And it would still be traveling now. And it would still be traveling for another 76,000 years. This is what space means. This is the quiet truth at the heart of all of these beautiful, humbling numbers. The universe is not scaled to human lives. It is not scaled to human ambitions. It is not scaled to human impatience. It exists on timescales so long that our entire history, from the first stone tool to the last word of the last language ever spoken, is a fraction of a fraction of a fraction of a cosmic moment. And yet we are here. We are aware. We are asking these questions, feeling this wonder, lying in the dark and listening to the silence between the stars. If the universe is vast, and we are small, then what we have accomplished, simply by existing and wondering, is extraordinary beyond measure. And now, in this deepening quiet, in this long, slow descent toward sleep, something shifts. Not the content of what we're exploring, but the way it feels. The numbers have done their work. They have expanded the mind, opened it outward, dissolved the cramped and hurried feeling of a day lived at human scale. And now the universe is beginning to do what it always does for those who truly sit with it. It is making you feel very, very peaceful. Let the darkness hold you now. We have come a long way tonight. We left Earth in the quiet of the early evening, or perhaps the middle of the night, or perhaps in that soft, undefined hour between late and early, when the whole world seems to have gone to sleep except for you. And we traveled outward, step by step, world by world, through the entire family of planets that orbit this gentle, middle-aged star we call the Sun. We skimmed the sun-baked craters of Mercury, that small and ancient world spinning slowly in the inner heat. We drifted through the sulfuric clouds of Venus, that beautiful, terrible twin of Earth, hiding its mysteries behind an impenetrable veil. We visited Mars, that red and dusty world of possibility, where ancient riverbeds trace the memory of water and the hope of life lingers in the cold beneath the surface. We crossed the asteroid belt and found it empty and quiet, not the dangerous gauntlet of science fiction, but the peaceful, scattered remnant of worlds that never quite came together. We were humbled by Jupiter, by its sheer immensity, by its great red spot and its moon Europa with its hidden ocean. We were dazzled by Saturn's impossible rings, those thin and fragile and ephemeral jewels that will not survive another 100 million years, that we are lucky to see at all. We visited Uranus, that tilted, quiet world of pale blue, rolling through its orbit on its side in a way that produces seasons no human concept of seasonal change can properly contain. And we visited Neptune, that dynamic, stormy world at the edge of the planetary family, with its backward moon Triton counting down the billions of years until its own dissolution. And then we drifted beyond the planets altogether, into the Kuiper belt and the scattered disk and the theoretical vastness of the Oort cloud, the sun's outermost domain, where icy worlds move in orbits so large that they take millions of years to complete a single loop. We looked outward toward the stars, toward Proxima Centauri, and the staggering truth that even our nearest stellar neighbor is so far away that reaching it at our current speeds would take 80,000 years. And through all of this, through all of these distances and times and wonders, something has been happening to the pace of your thoughts. they have been slowing. That is what the universe does, if you let it. It slows you down. Not with boredom or tedium, but with a gentle, persistent invitation to match your inner rhythm to something larger than the day-to-day. To breathe at the pace of geological time. To think at the pace of orbital mechanics. To feel at the pace of a comet falling inward from the Oort cloud for 100,000 years. There is a concept in astronomy called deep time. It refers to the incomprehensible length of geological and cosmological time, the billions of years that preceded us and the billions that will follow. When you truly absorb deep time, even just a little of it, it changes something in your relationship with the present moment. Because the present moment right now, this exact moment in which you are lying still and breathing slowly and letting the weight of the day release its hold, this moment is also a moment in deep time. This moment is part of the 4.5 billion years of this planet's existence. It is part of the 13.8 billion years of the universe's existence. This moment is ancient, and it is new. At the same time, every atom in your body is billions of years old. The hydrogen atoms in the water in your cells were formed in the first 3 minutes after the Big Bang, in an event so hot and so bright that no word in any human language is adequate to describe it. The carbon atoms, the oxygen, the iron, the calcium in your bones, these were forged inside stars that lived and died before the sun was born. Stars that burned for millions of years and then exploded in supernovas, scattering their material into space, where it slowly gathered over millions more years into the cloud of gas and dust that eventually collapsed to form our solar system. You are made of stardust, not metaphorically, not as poetry. Literally, physically, chemically, you are made of material that was once inside stars. You are the universe, folded into a temporary shape, lying in the dark, thinking about the stars that made you. And that thought, if you let it settle into the quiet center of your mind, is one of the most peaceful thoughts in the world. Because it means you belong here. Not just on this planet, not just in this solar system, but in this universe. You are not a stranger to the cosmos. You are part of it. You are a way for the cosmos to look at itself, to wonder about itself, to feel something about its own existence. Stars cannot wonder. Planets cannot wonder. But you can, and you are, right now. This is perhaps the most extraordinary journey in all of the solar system. Not the journey from Earth to Neptune, not the crossing of the asteroid belt, not the slow arc of a spacecraft through billions of kilometers of interplanetary space, but this one, the one that happens in the space between your ears, in the dark quiet of your mind, as you lie still and breathe and let the universe expand inside you. The distances we traveled tonight are real. The times are real. A spacecraft to Mercury can take 7 years. A spacecraft to Neptune took 12. The outer Oort cloud is a light year away. Proxima Centauri is 4 light years away. The Milky Way is 100,000 light years across. The observable universe is 93 billion light years in diameter. These numbers are real, and they are calming, because they remind you that you don't have to carry the weight of the universe tonight. The universe is doing its own work, orbiting and revolving, and expanding and cooling at its own pace, in its own time, according to its own unhurried laws. You can rest. The planets will continue their orbits without you watching. Jupiter's great red spot will continue its centuries-long storm without your concern. Saturn's rings will continue their slow, patient decay without your attention. Neptune's winds will howl on. Triton will spiral inward on its geological schedule. And somewhere in the Oort cloud, a comet is beginning a journey that will bring it through the inner solar system in 50,000 years, long after anything we have built or written or loved or feared has turned to dust. The universe is patient. You can afford to be patient too. And as the thoughts grow softer now, as the images begin to blur at the edges the way all images do in the final approach to sleep, let one more thought be with you. Every civilization that has ever existed on this planet has looked up at the night sky. Every civilization, from the very first human communities that gathered around fires in the African savanna, to the ancient astronomers of Babylon and Egypt, and Greece and China and the Americas, to the scientists and engineers and dreamers of the space age, every single one has looked up at those same stars and felt something. Something that cannot be fully named. Something between wonder and belonging and longing and peace. The same stars. The same darkness. The same ancient light, traveling for years and decades and centuries to reach your eyes. When you look at a star, even now with your eyes closed, you are looking into the past. The star you see is not where it is now. The light you see left that star years ago, decades ago, centuries ago for some. You are seeing the past. You are receiving a message from ancient history, delivered at the speed of light, arriving exactly now, exactly in this moment, exactly for you. The universe has been sending you those messages your entire life. And now, in this quiet, in this soft and deepening dark, you can simply receive them. You don't need to understand them fully. You don't need to remember all the numbers, all the distances, all the times. You don't need to carry this knowledge anywhere specific. You can simply let it rest inside you, like a stone settles to the bottom of a still pond, sinking slowly, touching the bottom, and then resting there in the cool and the quiet. The dark is not empty. It is full. Full of planets, moving in their patient ellipses. Full of moons, each one a world. Full of comets' beginning journeys that will outlast everything you know. Full of light from stars that may no longer exist, but whose light has not yet run out. Full of questions that humanity will spend centuries answering. Full of wonders not yet discovered, not yet imagined. And you are in it, right now, part of it. Rest in that. Let your breathing slow to the pace of tides. Let your thoughts drift like dust in the outer solar system, slowly, gently, following the gentle pull of gravity toward sleep. Let the images of planets and rings and icy moons and ancient craters and hidden oceans fade like the last light of a sunset, beautiful to the very end. There is nowhere you need to be tonight. There is nothing you need to solve. The solar system is 3 hours older than it was when we began, which means it is approximately 4,500,000,003 years old. And somehow, in all of that time, in all of that space, in all of that darkness and silence, and spinning and orbiting and colliding and cooling, something happened on one small rocky world orbiting one medium-sized star in the outer arm of a spiral galaxy. Something began to breathe. Something began to wonder. And tonight, in the quiet dark, with the universe wheeling overhead in its ancient patterns, that something is you, drifting now, carried gently, into the dark between the stars, into the silence between the planets, into the long, patient, beautiful night. Sleep well. The universe will still be here when you wake.